Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue with Chapter 7 on Categorical Data Analysis with Section 5 on comparing two proportions, independent samples. And about halfway through, there will be a discussion on conditional probability. So, as a motivating example, say that the New Mexico State Legislature is interested in how the proportion of registered voters that support Indian gaming differs between New Mexico and Colorado. So let's assume that we don't know what the true population proportions are in these states. And so we're going to have the state's statistician recommend that the state conduct a survey of registered voters independently in the two states and then compare those two proportions to see which state favors gaming more. So the statistical methods for comparing two independent samples proceed this way. So we're going to let P1 and P2 be the true population proportions in our two populations, and we're going to estimate P1 hat and P2 hat as the number of successes in each sample for our two populations based on representative samples of size N1 and N2. The formulation of confidence intervals and hypothesis tests are similar to previous sections in this chapter. In this case, where we're interested in the difference between population proportions, we're going to estimate that difference. So we're going to start with a confidence interval. To estimate the population difference, or rather the difference in population proportions of population 1 minus population 2, we're going to estimate each of the individual population proportions, P1 hat and P2 hat, and take the difference. That is our estimate of the difference, plus or minus a z critical value, which is based on the standard normal distribution. So if it's a 95% interval, z is going to be 1.96, for example. It's roughly, 2 standard errors. And then the standard error of the difference needs to account for both the variability or the uncertainty in estimating the first proportion and the uncertainty in estimating the second proportion. So this standard error is calculated down here, and it's effectively just the variance of the first population plus the variance of the second population, take the square root. Because we have independent samples, the total variance of the difference is just the sum of the variances. So that's why we see the sum of the variances under the square root symbol. And that's our confidence interval. Similarly, effectively by taking this expression and rearranging it to solve for the critical value, we get the test, the hypothesis test, the null hypothesis being that the difference equals 0, and the alternative being that the difference does not equal 0, that one proportion is larger than the other. This test statistic, z, it's actually very similar to the t statistics we've seen in previous chapters, except for proportions we use a z because we're looking specifically at the normal distribution instead of a t distribution. So this z statistic is the estimate divided by its standard error. The estimate is the difference in proportions, and the standard error is what we estimated as the standard error for that difference. You look at this ratio, and if this ratio is much larger than 2, so this z critical value is going to be 1.96 if it's a 95%, if our alpha level is 0.05. So that's what we'll use there. Okay. There are different ways of estimating the standard error for the test. Recall that under the null hypothesis, the population proportions are equal to each other. And so just as in a one sample test where we had a slightly different standard error, same here we can have a different standard error. So what do we use for our standard error?
Notice above when we did the confidence interval, we just plugged in our estimates for P1 hat and P2 hat. Well, down here, for hypothesis test where we assume that the proportions are equal, we need some estimate of what that equal proportion is. And so we're going to use this pooled proportion, and we'll just call that P bar, sort of like an average of the estimates. And they're just weighted averages. So N1 times P1 is the weighted average for proportion 1 weighted by the number of samples in the first population. Same thing for proportion 2, and we divide by the total sample size. So this is a weighted estimate or pooled proportion, and we use that in our estimate for the standard error. So instead of P1 hat and P2 hat now, we have the P bars, which is that pooled proportion. And you can rearrange this to simplify it, not that important. And so then from our z statistic, we can calculate a p-value and so on and draw conclusions about the how reasonable the null hypothesis is, or how much does the data support that hypothesis. All right, let's look at an example. So this is a famous example, and it's particularly back when I used to lecture this class, we would come around this when it would start to get cold outside, and people sometimes start taking vitamin C's to protect them from catching a cold. So here is a study of 279 French skiers who were studied during 2 one-week periods in 1961. During one group of 140 skiers received a placebo each day that they went skiing, and the other 139, probably there were 140 each, and then maybe one person skied into a tree or something like that. The other group got 1 gram of ascorbic acid, which is vitamin C, each day. And the study was double-blind, meaning that the subjects didn't know what treatment they got, and the researchers who were administering the placebo or the vitamin C didn't know what they were submitting either. So that is double-blind. Single blind would be only when the subjects are blinded. Double blind is when the researcher also doesn't know what they're actually prescribing. So let's let P1 be the probability that a member of the ascorbic acid group contracts a cold. Okay, so this is the probability of getting a cold. Group 1 is the treatment group for ascorbic acid, and P2 is the probability that the placebo group gets a cold. And we're interested to test, as is Linus Pauling, who developed discovered vitamin C, we're interested to know whether vitamin C has an effect on catching a cold. So our null hypothesis is that there's no effect, that the proportion of getting a cold for the treatment group is the same as the placebo group, and here is our data. So along the columns, we have the ascorbic acid group and the placebo group, and going down each column, we have the number with a cold. So 17 out of 139 is the treatment group, and placebo group is 31 out of 140. Now, on the face of it, as I look at this just without looking ahead at the results, 17 is almost just over a half of 31, right? And then we have about the same sample sizes. So just on the face of it, it looks like your probability is half for catching a cold if you're in the vitamin C group. Let's see what the results tell us. So the sample proportion of skiers with the cold, if we estimate these proportions, we've got, let's see, this P1 is our treatment group, that's 0.122, and in our placebo group, P2, that's 0.221. Now these numbers are a little confusing because they look like they're reverse ordered of each other. So let's just say 12% and 22% is the probability of getting the cold. The difference of those proportions is about 10%. And if you, under the null hypothesis of equal proportions, if you take that average, we get 17%. Okay, so we can calculate the standard error of that difference, which is about 0.045. Calculate a test statistic, so that's the vitamin C minus the placebo group divided by the standard error, which gives us a z-statistic of negative 2.19. So we're interested to know whether that's more extreme than 1.96, which is the 0.05 level. If we calculate the p-value associated with that, the p-value is 0.028, which is less than 0.05. Therefore, we state our conclusion in words and then in the context of the problem. So we reject the null hypothesis in favor of the alternative, concluding that the probability of contracting a cold is different for the placebo and vitamin C groups. All right. If we calculate a confidence interval, so we want to know basically how different are these two groups, we've got the same estimate, which was about 10% of the difference. We can calculate the margin of error as 1.96 times the standard error. Calculate all this out, we get 0.088, and this confidence interval is negative 0.099 plus or minus 0.088, and so the range is roughly negative 19% to negative 1%. And so we're 95% confident that the difference is in this interval. I really hate the definition of confidence. We're actually 95% confident that before we collect the data, we get a confidence interval that includes the true population difference between vitamin C and placebo group. Okay, but it looks like we have a negative difference here, which says that vitamin C reduces the French skier chance of developing a cold by somewhere between, say, 1% and 19%. And this conclusion's been somewhat controversial. I know that some of you will want to stop here and run out and get vitamin C. There's been future studies that say that vitamin C is not that useful, and that in fact it could just be that in this sample of 279 skiers that we just got an unlucky batch in that they weren't representative of the effects of vitamin C and placebo, and we by chance found a treatment effect where there isn't any. And there's a 5% chance that that happened. All right, here's how we do it in R. We've got a proportion test, and we've seen this code before in earlier sections where we just had one group where we had the number of successes and the number of trials. Actually, yes, we had number of successes on the left, and then as the second argument, the number of trials. So now we've combined the two groups, the number of successes. So we've got 17 and 31 are the number of successes for the treatment and placebo group, and then we have their sample sizes as the second argument, and we run the result. We get the p-value that we saw earlier of 0.028 and the 95% confidence interval here. Okay, and these are the S2 population estimates. Great. So that is everything you need to know for conducting this test. Perhaps we should revisit the assumptions. If I page up for a moment to this particular example, do we recall what the model assumptions are for a hypothesis test and confidence interval for a one-sample proportion test? So we had a rule of thumb that you need at least 5 successes and at least 5 failures, and we actually have that in this case. We have 17 successes and 122 failures, and so we have plenty of observation, success, and failure for this normal approximation to the binomial test to be accurate. So I feel pretty confident about this result. All right. The next section, and let me page down for just one moment. All right, we're going to see some plots. Is on conditional probability. So in probability theory, a conditional probability is the probability of an event that an event will occur when another event is known to have occurred. That was poorly read. So it basically means that the probability of one event sort of depends, possibly, on knowing some additional information about whether a second event occurred. Okay, so let's say we've got these two events, A and B, and we want to know the probability of A given B. So for example, how about the probability that it will rain this in the next hour conditional on it being cloudy. Okay, so that is probably a higher probability than the probability of rain conditional on it being sunny right now. So this sort of, here's the notation that we're going to use. Here's the probability of A given B. So this vertical pipe, which is the key, the shift key above your enter key and below your backspace, that vertical pipe, it means given or conditional on. So the probability of A given B may or may not be the same as just the probability of A alone. If A and B are independent of each other, for example, the probability it will rain conditional on me flipping this coin and getting ahead, I would say that the probability of flipping a coin and probability of it raining are independent of each other. One doesn't affect the other. And so if these two statements are equal, that means A and B are independent of each other. Otherwise, there's some dependence there. In particular, in the previous example, what we were testing is the probability of getting a cold, that's event A, is that conditional on whether you took vitamin C or a placebo? That's event B. And in the previous example, we concluded that, in fact, these probabilities were different. So the treatment, conditional on B, affected the primary outcome of getting a cold. And if I remembered my own notes, that's exactly what this says here. Perfect. So let's take a look at another example on cervical dysplasia. This is a case control study designed to examine the risk factors for cervical dysplasia. All women in the study were patients here at the University of New Mexico clinics. There were 175 cases who were women, aged between 18 and 40, who had cervical dysplasia. And we had 108 controls, women in the same age range, who did not have it. Okay, so we've got cases and controls. These are whether they had cervical dysplasia or not. And we had that 175 total or 308 total. Now we have another variable, which is the HPV outcome. So each woman was classified as either positive or negative depending on the presence of the human papillomavirus. Fairly not popular, a common virus for people to have. So let's take a short detour and look at how to create this table in R and then do some calculations, and then we'll come back to answering whether there's conditionality, or the probabilities here are conditional. Does one outcome depend on the other? So one way to make this table, and I apologize this breaks over the page, is to use the matrix function. In a matrix, you start with a list of numbers. So here's our list of numbers. I'm going to scroll up just a little bit so we can see the original data. That's the table we want to make at the top. And so our numbers, I'm just going from across the rows. So 164, 130, and then the next row 11 and 178. So the body of the table is what I'm inputting. And then I'm going to use commands to shape the data. So in this matrix, I'm going to create a matrix from this list of numbers. The number of rows it will have is 2, and by row equals true. The default for matrices is to go down the columns. So if I had specified these numbers in the order of 164, then 11, then 130, then 178, it would automatically do this in the order that I want. But I need to specify that I'm going across the rows when I'm shaping this matrix. So by row equals true. So that alone will create, if you close parenthesis after by row, that will create the table. I always find it helpful to label a table. So we can also specify dimension names, and we specify first the row, then the columns. So I'm going to create a list, and this has a somewhat particular syntax. The first thing in quotes, HPV.outcome, is the title for the rows, and that equals, and then I combine and create labels for each row. So we got positive and negative, just like up here. Then I put a comma, and then I'm going to label the columns. So then I've got two groups, equals, and the labels for each column are cases and controls. So now the HPV object has our data in it, and it has perfectly labeled rows and columns. All right, so now we can use prop table to calculate proportions, and there are different ways of calculating proportions. If we just do prop table of HPV, I believe it makes all the numbers in the table sum to 1, but we actually want margin equals 2, which will calculate, so the margin equals 1 would be that proportions along rows sum to 1, but margin equals 2 makes numbers along columns sum to 1. So this is basically saying, conditional on being a case, what's the probability of being positive for HPV? Okay, and conditional on being a control, what's the probability of being positive for HPV? So the conditional probability we're looking at is, what's the probability of being HPV positive, conditional on which group you're in. Right. So in order to do some analysis, we need to reshape this data that's in wide format into long format. We can use that using the reshape2 function and melting the data. And it's as easy as this. You put in the HPV data set, and then you specify, in this case, what the, actually I think it just sort of works. The only thing that's happening here is I'm labeling the numbers. All right, so what's happening? Let me scroll up for a moment and point some things out. Here's our HPV table. And when I reshape this, it's going to take the first row, which indicates positive and negative, and create a column for those. It's going to take the column labels, the group, cases, and controls, and create a column for that. And it's going to create a third column which has the actual values in it. So if I scroll down a little bit, I can just barely get both on the same screen. So here's the first column, HPV outcome. We've got positive and negative. Then on the second column, we have group, which are cases and controls. And then the third column are the frequencies. And the name frequency, I needed to specify the value name. All right. So now each row and column is uniquely identified and given the frequency. And now we can do some analysis with it. Notice we can recover our original table with crosstabs by counting up the frequencies based on HPV outcome and group. So here's our original table again, as well as a proportion of that table. Okay, so all right, so we've learned some things about reshaping. Given our proportion table, we can also melt the data to get these proportions as numbers. Okay, so here's the HPV column proportions in long format. This is this table. And we can take the two data sets, the one with frequencies and the one with proportions, and join them together by the HPV outcome and the groups. And so here is our full data set with outcome, group, frequencies, and proportions. So there's lots of ways to have created this column, this table, and I'm just showing you some ways of getting comfortable with moving from one format to another and calculating different values. All right, let's look at some plots. And we should critique some of these plots because there's lots of ways to visualize data, and some will communicate to us better than others. All right, so let's just scroll down and look at the plots first, and we'll come back and take a look at how we made them. Can we get all these? Yes. All right, here's 4 plots of the same data. So on the left, top left, we have the cases and controls on the x-axis. We have the frequency on the vertical axis, and we've got 2 colors. Red is positive, blue is negative. So here we've got, in the cases, we have tons of positives and very few negatives, whereas in the controls, it's not half and half, but maybe 40-60 for positive and negative. The other 3 plots have to do with proportion. So if we scroll down to the bottom left, now we've got proportion on the vertical axis, and these red and blue bars for each cases and control should add up to 100% or 1. So you can imagine stacking this blue bit on top, and that would sum to 100%. In fact, that is what the top right plot does. So we have a single bar colored red and blue, and I really like this plot when there's only 2 groups and when the success category, so in this case positive HPV, starts at the bottom, so that then you can read up to the boundary, and that is your probability of success, around 0.95 or something. If the blue and red were swapped here, I wouldn't like this as much, because then you're measuring sort of the probability of failure. Okay. But when that's not when that's not the case, or when you've got more than 2 categories, I think this plot on the left is not bad. Okay. Finally, on the bottom right, we have dots instead, and so we've got the red dot is positive and the blue dot is negative, and you can see that these dots basically correspond to the tops of the bars in the plot on the bottom left. And one feature that this has is we've connected the dots between the groups to show what the difference is in success. So the success was around 0.95 and it went down to 0.4 between the 2 groups. In terms of the negatives, you can measure that with the blue one. Among these 4, which one do you think works best for you? I guess I'll say that I sort of like the one in the top right because the data in this case is not very complicated, and the red bars tell me what I need to know. All right, so if we take a look at the code for this, the plot in the top left was this first plot. The stat identity position dodge made the bars, and we're also plotting y equals frequency. That position dodge is what we see on the left-hand side. So the bars are dodged, so they each take their own space. Okay, those are those 2 plots over there. Okay, so that other bottom plot is this proportion, and oops, I'm sorry, I'm jumping around. All right. Oh, that's this one here, proportion dodge. All right, so this is plot 3. For plot 2, the top right, that was proportion and stat identity. That stacks them up. So they stay over the label, meaning over the cases label, they stack up in the same location until they add to 1. And then the bottom right plot with the lines, we're plotting points and lines here. So, and we're creating groups, which are the HPV outcome. So all the lines connect the HPV outcome. So the HPV outcome of positive draws a line, and the group of dots to connect are all the positive ones, and then all the negative ones. So the grouping indicates which dots are connected with lines. Okay, so all that. Let me scroll way back up and revisit the problem, or the question that we have. So we want to know what the relationship is in terms of conditional probability about the HPV outcome relative to your cervical dysplasia result either whether you're a case or a control, meaning whether you have cervical dysplasia or not. I'll page back down, and we'll return to that hypothesis test. Just based on, say, this plot on the top right or on the bottom left, it looks like this probability is very different. It's almost a 50% difference, maybe even slightly more than that. So that's quite a remarkable difference between these two groups. Let's see what the result of a hypothesis test tells us. So let P1 be the probability that a case, that's someone with cervical dysplasia, is HPV positive, and P2 be the probability that a control is HPV positive. We've got our sample sizes, we've got our estimates of about 94% versus 42%. Our standard error, if you plug everything in for a confidence interval, so we're plugging in our estimates here, gives us a standard error of 0.066. So our confidence interval for this difference is about 51% plus or minus 6%. So the difference is somewhere between 45% and 58%. That's a huge difference between two groups. All right, if we can use the prop test to do this for us in R, here's the number of successes for our two groups, and here are the sample sizes for the two groups. We're asking a two-sided hypothesis test of whether these proportions are equal. We have a huge chi-squared statistic with 1 degree of freedom, a p-value that's smaller than the minimum value that it will be reported. So the p-value is basically 0 here. And this is the confidence interval that we calculated. All right. Just to remind us that we can do one-sided tests as well, what if we a priori, so before we observed the data, what if we assumed that, maybe we'll just look at a plot, what if we assume that cases are more likely to have HPV than controls? Then we would want to calculate a one-sided confidence interval, perhaps, or maybe do a hypothesis test where the alternative is that the null hypothesis is that these proportions are equal, and the alternative is that cases is greater than controls. How would we do that? So I page back down. The group that we listed first are the cases, so we're interested in the alternative of greater, that first group is greater than the other. We have a chi-square statistic that's basically the same as before, and we still reject with a p-value that's basically 0. And then we have our 95% confidence interval, and notice that it is one-sided. So we're 95% confident that the true population proportion is basically greater than 0.46. And we don't have an upper bound. We only have a lower bound because of the direction of our alternative. All right, so what is the appropriateness of our test? Just like before, we need at least 5 successes and at least 5 failures in our samples. And this was fine for both of our examples. And that's the end of this section.